Hi, this is where we left off in the last class, so let's pick up right where we left off. The probability of an event is a number between 0 and 1 that expresses the likelihood of that event occurring. And so we have looked at the notation for probabilities, which is what we have over here. To calculate probability, we have three ways that we can do so. We have three rules that we are going to be looking at. So the first one is relative frequency approximation of probability. In this case, you carry out the experiment a certain number of times and you record how many times the particular event occurred. The ratio of the number of times the event occurs to the number of trials carried out, well, that's going to give you your probability. So a classic example would be this one here. If you want to know the probability of this thumbtacks landing as you see it here, as opposed to landing, lying down, well, you cannot use this other approach, which we will discuss right now, because, well, the outcomes in the sample space are not equally likely. What are the outcomes here? Well, it can either land pointing straight up like this, or it can land lying down. Obviously, those are not equally likely. So you can't just say the probability of landing like this is 1 out of 2. So what you need to do is toss this thumbtack several times, the more the better, and record how many times it lands this way. The law of large numbers is telling us that the more you carry out this trial, the more you do this, the closer to the real probability you're going to get. If we throw a die and we want to know the probability of getting a 1 as is shown here, well, what we do, since this is a fair die and all the outcomes in the sample space are equally likely, we can use this approach, which simply takes the number of ways that the event can occur, in other words, the cardinality of the event, which is a subset of the sample space, and we divide that by the cardinality of the sample space. In other words, the number of ways that, the number of outcomes that you can have. Remember, you can only use this approach when all the outcomes in your sample space are equally likely. So keep this in mind. So of course the probability of getting a 1 then would be 1 out of 6, because, well, there is only one way to get a 1 and there are 6 possible outcomes. The third rule that we could use is referred to as subjective probability, and this is the approach used by experts in various fields who look at a lot of data, and then based on their experience they come to some conclusion and they make some sort of prediction. A classic example of this is weather forecasting. Different meteorologists can look at the same data and one person will conclude, well, tomorrow there is a 20% chance of rain, and another meteorologist might say, no, I think it should be 30%. So we won't be looking at this approach much in this class. Here we have one more definition: the complement of an event. The complement of event A, and this is how it is denoted, consists of all outcomes in which event A does not occur. So remember, your sample space is a set of all the possible outcomes. The event A is a subset of that sample space. The complement of event A are all the elements in the sample space that are not in that subset A. One example of this would be, let's say, the throwing of a die. The sample space would be 1, 2, 3, 4, 5, 6. And let's suppose we're interested in getting the number 3. Well, that event would have one element in it. What would be the complement of A? Well, it would be all elements in the sample space except for those in A. And of course then this would be 1, 2, 4, 5, 6. the probability of A is 1 out of 6. Notice the probability of the complement of A is 5 out of 6. Note also, and this is very important, that the probability of the complement of A is 1 minus the probability of A. And the other way around, the probability of A is 1 minus the probability of the complement of A. But let's just leave it like this. Probability of the complement of A is equal to 1 minus the probability of A. We can apply this to this example here. In reality, more boys are born than girls. In one typical group, there are 205 newborn babies. 105 of them are boys. So you have 205 newborn babies and 105 of them are boys. If one baby is randomly selected from the group, what is the probability that the baby is not a boy? So now, notice we are not using the classical approach here, because the classical approach would say, well, the outcomes are boy, girl, there are two, the probability of any one of them would be 1/2. That's not the case here, because the outcomes are not equally likely. That's what this is saying here when it says, in reality, more boys are born than girls. So, again, in one typical group, there are 205 newborn babies, 105 of whom are boys. If one baby is randomly selected from the group, what is the probability that the baby is not a boy? Well, if you want to know the probability that the baby is not a boy, one easy way to do that is to simply find the probability that the baby is a girl. And of course, if 105 of the babies were boys, then 100 were girls. So notice this is using the relative frequency approach. So 100 out of 205 is 0.488. Let's now look at some examples. The first one reads as follows. Find the probability that NBA basketball player Reggie Miller makes a free throw after being fouled. So at one point in his career, he made 5,915 free throws in 6,679 attempts. So how are you going to calculate this probability? Well, you cannot use the classical approach, because in that case, the sample space would only have two outcomes. Either he makes it or he doesn't. And if you use this classical approach, then you'd say, well, the probability would be 1/2. And obviously, that's not going to be the answer. So we have to use the frequency approach. So in this case, how many successes did he have? He had 5,915. And the total number of attempts was 6,679. So the probability then is 0.886. In this example, you're told that as part of a study of the genotypes, and the 4 genotypes are listed here, you write each individual genotype on an index card, then you shuffle the 4 cards and randomly select one of them. What is the probability that you select this one? Well, here we can use the classical approach. The sample space consists of these 4 elements, and the event has only one element in it, and that's this one here. And so the answer then is 1/4. In this case, we're told or asked, what is the probability that your car will be hit by a meteorite this year? And so in this case, there's absolutely nothing to go on except just your intuition. So a reasonable estimate, I would think, and of course this is totally subjective, is, let's say, 1 in a trillion. Very small number. And so that's what is being written here. And it's based on your general knowledge. It's based on the fact that you've never heard of a car being hit by a meteorite. You watch YouTube videos, you've never heard of it. So or maybe you've heard of one. And so if that's the case, maybe you find 2. I don't know. I haven't actually looked for this on YouTube. But as you can imagine, this is something very rare. I know I've definitely never heard of it on the news. In this example, we're told that adults are randomly selected for a Gallup poll, and they are asked if they think that cloning of humans should or should not be allowed. Among the randomly selected adults surveyed, 9-1 said that cloning of humans should be allowed. 901 said that it should not be allowed, and 20 had no opinion. Based on these results, estimate the probability that a randomly selected person believes that cloning of humans should be allowed. It should be clear by now that you cannot use the classical approach to this. If you were to do that, your sample space would be yes, no, no opinion, and then selecting any one of them would simply be 1 out of 3. That obviously is not acceptable here. So we need to use a frequency approach. Now, instead of just working with values from the paragraph like this, you should always organize your values in some way, something like this. And so this gives you a clearer picture of what's going on. You have 1,012 total responses, and then 91 responded that yes, cloning of humans should be allowed. And so then, to answer this question, we simply divide 91 by 1,012, and we get 0.0899. In this example, we're asked to find the probability that when a couple has 3 children, they will have exactly 2 boys. Assume that boys and girls are equally likely, and that the gender of any child is not influenced by the gender of any other child. So now we're getting into a problem that's a little bit more involved. We're going to use the classical approach. And remember, to use the classical approach, you have to have some sense of the sample space. So here we're going to enumerate the sample space because it's not that big of a sample space. Here is the sample space. Note we have 8 elements in the sample space. There are 8 possible outcomes. Boy, boy, boy. In other words, the first child is a boy, the second child is a boy, the third child is a boy. And we can go on like this. We can have the first child is a girl, the second child is a boy, the third child is a girl. So these are all the possible outcomes. And how many elements do we have here? We have 8. The event is having 2 boys, and so remember, the event is always a subset of the sample space. And in this case, we have boy, boy, girl, and we have boy, girl, boy, and we have girl, boy, boy. And so these are the only ways that you can get exactly 2 boys. And so then the cardinality of the event is 3. The cardinality of the sample space is 8. So you're beginning to see now how this is getting a little bit more complicated. It's not just the probability of getting an even number when you throw a single die. And it's going to get a little bit more complicated as we move along. So I hope you're getting this idea and learning to think in terms of events and sample spaces as sets. And we're working with the cardinality of these sets. Note very carefully that we are not really interested in listing all of this out. We only want to know how many elements there are in here. Same goes for this. We are only interested in knowing that there are 8 elements here and that there are 3 elements here. So this brings us to the idea of counting. We need to know how to count effectively. And by counting, I do not mean saying 1, 2, 3, 4, 5. I mean knowing how many elements there are in the set, for example. So let's suppose it's not 3 children. Let's suppose it's 8 children. You would not want to have to list this out for 8 children. So what you want to be able to do is say, well, how many elements would there be in a set like this if there were 8 children? And if I was asking for exactly 2 boys, well, how many of those elements would have 2 boys? And so this is why counting, or combinatorics as it's otherwise known, becomes very important. So as the questions become more difficult, you will not be able to list out the entire sample space, because quite literally the sample space can have millions, billions, trillions of elements. And so you need to be able to find more sophisticated ways of figuring out the size of the sample space and the size of your event. And so we'll be looking at that a little bit later on. I forgot to put a little comma here, so let me do that now. There we go. Alright, so this gives us 3 hits. Our final example is as follows. If a year is selected at random, find the probability that Thanksgiving Day will be on a Wednesday, or Thursday. And so this requires some knowledge of what Thanksgiving Day is all about and when it occurs. And so, by definition, I guess we can say Thanksgiving Day always falls on the fourth Thursday in November. So the probability of it falling on a Wednesday is 0 because it can't happen. What's the probability of it falling on a Thursday? Well, it has to fall on a Thursday, so it's going to be 1. So this is just to recap something we've said before. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. All probabilities exist on a continuum between 0 and 1 inclusive. Notice equal, less than or equal, less than or equal. And so the probability can go from 0 to 1, including 0 and 1. So this brings us to the end of this presentation. So make sure you go over this carefully and answer any questions that I posted. Okay, so bye for now.